Hello everyone, and welcome to today's lecture on audio effects, theory, implementation, and application, where today we will be talking about the audio effect vibrato. It's an interesting one because it's known primarily as a playing technique, and so it's only later that it was implemented as a digital audio effect with signal processing. Let's see. So what do we mean by vibrato? Well, the textbook definition is small, quasi-periodic variations in pitch of tone. It doesn't have to be an exact period. There can be some variation in the repetition. And the typical depth of vibrato is on the order of 1%. So this means that a pitch of, say, 100 hertz might only vary between 99 and 101 hertz, on the order of 1%. On the order, though, it could be a lot more, a lot less than that. Vibrato is often accompanied by tremolo, which is amplitude modulation. Somewhat simpler effect, it's just changing the level of a signal, but modulating that in a quasi-periodic, or just a quasi-periodic way. Now, how do we apply vibrato? We can exactly model the performance technique of varying the string length with one's fingers to have the frequency vary back and forth by modulating a delay line. So if the audio is being delayed and you make the delay smaller or longer, then what happens is it takes different amount of time for a signal to traverse that string, and hence varies in the pitch of the sound being produced, because the pitch relates to the period, or in turn the frequency, and the period changes by changing the distance that a point on a sound wave needs to travel. This is the same basic idea as Doppler shift as you would have covered in physics classes as well. So I mentioned it is a playing technique. Consider violin. Vibrato is produced by wiggling the finger as one plays violin. This results in changes where the string is stopped on the fingerboard, and the vibrato frequency is quite slow compared to the audio signal and its frequencies. So a vibrato of 6 hertz, 6 times per second, wiggling that finger, is quite slow compared to 100 hertz, 400 hertz, and up to a few thousand hertz as well. The frequency modulations of the string vibrations also produced amplitude modulations. So when the finger is pressed down on the string, it affects the frequency response of the violin body. Vibrato can also be produced in singing voice as well by modulating the tension of the vocal fold. So a singing technique as well as a performance technique. Let's give an example of vibrato. And here we'll have first a note played no vibrato, same note with vibrato, and then to show how vibrato can interact with other effects, we first play the same note, but no vibrato and with reverb, and then we play vibrato and reverb together on the same note to see how the effects combine. So here we go. Now, I think the vibrato and reverb is a far more intense effect, whereas going from no reverb, no vibrato to just with reverb is not as intense. So it's a combination of the vibrato and the reverb, essentially modulating every single um, uh, echo, every single um, copy, delayed copy, and attenuated copy of the of the signal within the reverberated signal. So how is it implemented? It's just a delay line, but the trick is to vary the delay in the delay line. So when the modulation that is being applied is something like a sinusoid, then that's similar to the modulation of a finger wiggling on a violin, or the modulation that a singer might do with the vocal cords. So it's somewhat smooth in its behavior. It's not jumping like a square wave might from one value to the next. And the variation, the frequency of this modulation is controlled by a low frequency oscillator. Also, we need a fractional delay because here we're continually varying the delay. So what happens if the delay is, say, more than 5 samples but less than 6 samples? So, why don't we talk about these two new concepts we're introducing here? Let's first talk about the low frequency oscillator because it didn't occur in basic delay and didn't occur when we were discussing MIDI or a noise source. So bear with me 1 second and I'll bring up some specific slides on LFOs. Okay, let me just check if you are seeing this too. Yes. Okay. LFO is just a low frequency oscillator. It does not specify the form the oscillator takes, and oscillator really can be any periodic signal. But there are common signals that are used over and over. The sine wave, in fact, I'll see if I can fix this. Okay, 1 second. Making some minor edits to the slides. Okay, so we have the sine wave, sinusoidal, as you know, triangle wave or triangular wave, which forms the shape of a triangle and then repeats the same shape over and over. The square wave, so it simply jumps from one value near the top to another value near the bottom, back and forth. And then we have the sawtooth wave, which looks like a triangle wave, except at that point where it starts to change from a positive slope to a negative slope. The negative slope is just an immediate drop down to its lowest possible value, and then it finds a way to move forward again. So these oscillators you will find over and over, and they're not that complicated ones. But generally, every effect that uses a low frequency oscillator will use one of these or some variation of these, and depending on the effect, there may be a preference for one over others. In our case, with vibrato, we already know that the sinusoid is often used. So how do we implement the low frequency oscillator? What we basically have is an oscillator that needs to vary from one sample to the next. So it can be implemented the same way we can have a VST instrument or plug-in instrument that is generating sinusoids. When we looked at MIDI and a monophonic synthesizer, that was generating, and what makes it similar is that you just keep track of phase and increment phase wherever you need to. So we have a function get LFO sample, which is used to calculate biased LFO waveforms with output range 0 to 1. So the phase range can be 0 to 1, and the output is also 0 to 1. What do we mean by biased? Well, our normal functions all have average values at 0. They're all symmetric around 0. But in this case, we can have a biased waveform like the ordinary sine function, which is essentially um, a function whose range is only from 0 to 1. So this is different. We are, the normal sine function is from -1 to +1. But here we have four functions whose form is only from 0 to 1. That might be a better explanation. So we have this function get LFO sample. We also now need to put this into a plugin. So we add private parameters to plugin processor.h. These private ones include things like LFO phase and the get LFO sample that we just looked at before. So these are the things that can be called over and over. We need to get the LFO sample depending on the phase, and we have the phase of the LFO. Then in the process block, we specify some value, call it LFO value, which involves getting the LFO sample as needed to check things. In the process block, we update the LFO phase every sample, also keeping that in the range 0 to 1. So when it exceeds 1, it simply wraps around back to 0 or 1 minus that value. So we'll see this LFO in action when going through the vibrato in detail. But the things to keep in mind are as follows. We have a get LFO sample. Let's see. Yes, the thing to keep in mind, we have a get LFO sample, which for any phase and waveform tells us exactly what the value is. We have private parameters in the plugin processor.h, the LFO sample, and get LFO, the LFO phase and get LFO sample. In the process block, we simply increment the LFO phase each time, and so we're able to sort of track the change in the LFO. Okay, so that is LFOs, but there are two things to keep in mind here. We mentioned the concept of fractional delay. What do we mean by this? So in the digital world, everything is discrete, which means we have samples at specific times. So sample x0 at time y0, sample x1 at time 1. Sometimes it's possible that these x's do have a nice linear relationship on y, But the idea is if you are somewhere between these two inputs, sample, say, call them sample 0 and sample 1, then what should that output be? And if it's a linear interpolation, if you're halfway between them, then the output would be the average of the inputs. And usually you're not perfectly that way, but it's something that we can keep track of and work with, and it's a suitable approximation for many problems. At the end of this, we will give a demo where this linear estimation works perfectly fine. So, fractional delay. What we've talked about is when there is non-integer delays. So, like if the delay is modulated but using a sine function. Um, First attempt, the zeroth order interpolation, is what's also known as near neighbor or nearest neighbor, where to estimate the value at some x between x0 and x1, you just pick the closest of those two values. So supposing this value in between was slightly closer to x0, then you assume that the value is y0, and you let it play constantly, and then it jumps to the next value. Um, that gives an approximation, but it's not a great approximation. So first order interpolation, which is what I showed a couple of slides earlier, is just a weighted sum of the two nearest points. So we assume that x0 and x1 are on a line. Then we fit the points to that line. So if we define the line as a times something plus b, we can define x1 and x0. And yeah, that's the basic idea of first order. The math is also fully explained in the book. Then we have quadratic interpolation. So think of these 3 points in red here as known. Let me back up. Think for first order, the 2 points before and after are known. So how does one estimate x? If um, if we know x0 and x1, then we can predict what it should be, what the output should be for some value in between them as well. Quadratic does the same thing, but tries to estimate, rather than a linear function, a quadratic function based on 3 nearby points. If you pick the values of 3 nearby points, you should be able to almost always, or most of the time, we will get, let's see how I say this. If you pick 3 values, say x of minus 1, x of 0, and x of 2, x of minus 1, time minus 1 times 0 and time 1, then almost always you will be able to fit the values between them to a quadratic curve based on just those 3 points. And they don't even need to be the closest 3 points. You could have minus 1, 0, and 2. You could still fit a quadratic function. So if we assume x is a function of time here, or it's equivalent to the y versus x shown previously, then you can fit a function a times some value squared plus b times some value to the 1 plus c, and then based on that you can derive the a, b, and c and get the values of the quadratic function, and so for any time you can determine what x would be. You can do similar things for a cubic function, and some people use cubic function, but I've generally found that if implemented correctly, quadratic function is absolutely fine for most audio. So, moving back, how does one work with fractional delay? Well, you recall that with delays, we generally have a read pointer and a write pointer. Um, and so what if you want to essentially read a value between nearby values? You do the same thing as done previously, only now you interpolate these nearby values here rather than bizarre k or y and so on. And yes, here's where we do linear interpolation. I'm just going to this is the line where the linear interpolation is done. If you recall, y of n equals 1 minus t times the delay line of previous plus t times the delay line of the next. And this is going to give us the value that we're most interested in. And then finally, we have interpolating the sample. So we have a routine associated with a plug-in audio processor. Okay. Let's see. Yikes. I need to make sure I am showing the right one. Fractional delay. So nearest neighbor, that's the zeroth order, just picks whichever of the sample before or sample after is closest to what we're interested in. Case 1, the first order or linear interpolation does exactly what we've just been showing. And second order or quadratic, a bit more math, but essentially it's interpolating a value by fitting a quadratic curve to 3 nearby samples. So now we have covered fractional delay and LFOs. Typical values that we deal with for vibrato have an average delay between 5 and 10 milliseconds and a frequency 5 to 14 hertz. So when one thinks about fingers moving, it's fairly fast, but compared to audio, it's very, very slow. 5 to 10 milliseconds allows a delay that you can then vary suitably to produce that the delay value can change suitably to produce the frequency shift one expects with vibrato. And that is vibrato. We can do a bit of math here. We can calculate the effect of changing delay and can actually predict what it does for different LFOs. So let's start with the trivial case. Supposing the delay is constant. We're not changing delay at all. So we have a delay which is some constant value m, and so when x changes from one value to the next by one sample. The output samples are also still one sampling period apart. Now, suppose the delay is always increasing, which it can't do indefinitely, but let's suppose it is the case. Then let's supposing it's increasing by zero point 0.1 each time. So it starts maybe a delay of one sample, then 1.1 samples, then 1.2 samples, and so on. So if one goes from one sample to the next, yeah, then what you basically have is that output samples are 0.9 times the sampling period apart. So the delay is always increasing, and so on, which means there are less samples for one cycle of a sinusoid. So increasing the delay gives a longer period, right? That's intuitive. Well, longer period gives lower frequency, which means that the pitch shifts down. On the other hand, decreasing the delay gives a shorter period, which results in a higher frequency or a pitch shift up. Um, So now consider a few of the other aspects. So vibrato, the maximum frequency deviation. The so determining the width or maximum frequency deviation of the vibrato, essentially if it goes from 90 hertz to 110 hertz, the extremes of that vibrato, essentially 10 hertz either way from an average, um, that depends on the LFO frequency and the sweep width. So let's take an example where the LFO is some form of sine wave. It has an average delay M, a sweep width W, and a frequency F. This can be written as M plus W times sine of 2 pi ft equals the delay of d of t. Let's look at the derivative of that. That tells us essentially the speed of change in position between read and write pointers. It's a bit like a difference operation, d of n minus d of n minus 1. If we take the derivative with respect to t, then that d of t becomes the derivative of d with respect to t equals 2 pi f. So those terms go outside the sinusoid times w times cosine 2 pi f. The right pointer, in this case, how we're putting samples down on the delay line, always moves at a constant speed, but the speed of the read pointer is what changes, and that determines the pitch shift. Here, if one looks at the derivative between the original total delay and its derivative, it's still sinusoidal variation. It's just a cosine function rather than a sine function. Let's have a look at some of these. So here we have the LFO waveform is a sinusoid. And then the pitch shift that results is also sinusoidal. Granted, it's at different frequencies, but that's not necessarily a problem. And if one increases the LFO, then that can also be a similar. Okay, so we looked at sinusoidal LFOs, where a sinusoid for the LFO also gives sinusoidal behavior for the pitch shift, and if the frequency increases, then the pitch shift increases. Sinusoidal LFOs are certainly the most common to use for vibrato, but what if a different type of low frequency oscillator was used? We could have the triangle waveform, for instance. then if one wants to take the time derivative of that triangular one, what one sees is that it first has a positive slope, then a negative slope. Positive, then negative. And so it's a constant value above the original pitch and then a constant value below the original pitch. And it toggles back and forth depending on whether you're on positive or negative slope. And if you want to look in detail, that is just how so, how does one implement Vibrato? We'll do it as a VST plugin. We can start with the delay plugin that was created previously and add methods for the low frequency oscillator and interpolation, which we talked about as well. In the process block, we have a loop for the samples, and within that loop is a loop for going over every channel. So only once we have gone through every channel do you increment the pointer once for the next sample. Same sort of steps as we usually take for any of the plugins here to create a new one. We first change the private parameters. So we have some floating point style parameters for values like sweep width. Then we also have some choice parameters. We can select from a short number of options the type of LFO and a small number of options the type of parameter. And we keep track of the phase as we increment the low frequency oscillator, just as before. So, first, what we've done here is define the parameters that we expose on the interface, and after determining something for the phase of the LFO, we have the parameters associated with the circular buffer because this is all using delay. Okay, so we start with the delay plugin, we change the private parameters, and then we set up the interface. I'm going to jump ahead a little bit to have a look at what goes on in the process block. Where in the process block, after some sort of standard lines in the beginning, we get the exposed parameters on the interface. So the type of LFO, the frequency, and the swell width. And we specify what the interpolation type will be. Then we go through all of the samples and all of the channels for each sample. We specify what the current delay will be, that's independent of the channel, as well as the delay read position as a function of the write position. Generally, we've written things in a very similar way as to the deblock procedure here. Yeah. Let's see. Finally, if we look at what is actually happening when we process each sample and each channel of each sample, this is it right here, where the read position is a function of the write position, and the actual amount of delay is given as current delay, which increments depending on the amount of delay that should be used, our modulated delay, and the read position is a function of the current delay. So the read position sort of varies in its distance from the write position. On average, it moves the same as the write position, but sometimes faster, sometimes slower. So let's have a look and see what this is going to be like. This is where we iterate over the channels, and that should just about cover things for the process block. Yes. So now I'm going to be quick and not go through bringing up Visual Studio because we can see the main changes here already. In the header file, we should have a few lines of code down here for the new methods and parameters that we need to work with. The few that are exposed on the user interface, we use the formal parameter like Josh adult input. So let's go. Here is where the parameters for the user interface are added. We change a few lines in prepare to play. Yep, for essentially allocating the buffer and the sweep width. And finally, we have the lines associated with um, the delay line modulation, just as was shown in the slides that were presented. Let's look at this in action. Ah, you may not have seen all of that. Oh. Okay, as mentioned, we can have a look at the files here. We're not using the plugin editor because we have the generic user interface. In the plugin processor header file, we have the parameters we expose on the interface, the parameters as well for defining and creating the circular buffer, and methods for interpolating samples and getting an LFO sample. Then if we look at the plugin processor, in the constructor, we set up the user interface. And in prepare to play, we set up the buffer. We already have the parameters, but now we specify just how big it is. And the initial phase of the LFO. And then we have the lines associated with the process block. So the implementation of modulating the delay, just as shown. Finally, we can see or listen to what this does in action. So bear with me. Lots of little mistakes in my naming of things, but here we have our tester plugin, as was used in the basic delay before, and Vibrato. And first, we'll go ahead. So we have the tester, which again we used with basic delay as well as vibrato. And we're going to set it to a sinusoid because we want some continuous signal that can be modulated in pitch. And we will bring this into vibrato, and from vibrato to the audio output. Okay, now you should already hear some vibrato, but it's not obvious. Let's switch to sine wave, and linear interpolation should be fine. LFO frequency is quite low. What if we speed it up? Changing the sweep width. So you might have noticed something. I'll kill that. Um, Something that sounds a bit like a police siren. And in fact, police and ambulance sirens generally are created by modulating the pitch of a sinusoid or similar signal. A nice thing about that is when the pitch goes up and down, if one thinks of the Doppler effect, it's like when the sound of a vehicle is coming towards you and away from you, back and forth, which means you can't tell exactly where it's coming from. You can't tell for sure, oh, I don't need to get out of the way because the ambulance is moving away from me, because it simulates Doppler of coming towards, coming away, and that means no matter what you're doing, you need to pay careful attention. So it's intentional that sirens operate this way because it makes it more difficult for you to tell where the vehicle is, which is what they want. It forces you to pay attention. Okay, so at that I will stop for today, and that concludes discussion of vibrato. Thanks very much.